section, we are going to now look at functions, and I can't really, that's a bad word, expressions that are written, that cannot be written in the usual fashion. Now we call them implicit versus explicit. So let's look at the ones that we can do. The explicit format, the explicit form, are the types of functions that would be this. I'll give you an example here. If I give you x times the cosine of y is equal to 1, explicitly I want to be able to say y equals. If I can say y equals, then I am able to use all the rules that I know about, and there's nothing different about this than any other problem that we've seen. So in order to do this, I probably would say cosine y equals 1 divided by x. And I'm going to let y be my output, let x be my input. And the problem that you might think that we have here is, I got cosine y. What am I going to do with that? How do I undo a cosine function? Well, if you've had trig, and most all of you had that, you probably know that any function can be reversed. You got an inverse for any function. Remember that the input of any trig function is the angle measure, and the output is the ratio between two sides. That was on the test. So if I'm going to look for y, I'm actually saying that my output now is going to be the angle. I want to know what is the ratio for the cosine function. What is the angle that would give me that ratio? And so we look at what we call arc cosine. We have arc sine, arc tangent. We're looking at arc cosine, in this case, of 1 divided by x. And so in this case, my input is the ratio and my output is the angle. It's the inverse function. Can I do this? Yeah. Did I write it as y equals? Yeah. So there's no big deal. We don't know, we didn't talk about the derivatives of inverse tangent functions like arc cosine, but it's just one of those other rules that we would go back and look up and be able to use. No big deal. We can look at some others. What if we had y cubed, and I'll just write it here. Let's see, y cubed minus x squared minus 2 divided by x squared plus 1. Actually, that is y cubed equals. Can I write this as y equals, not y cubed? And yeah, I just need to have the cube root of that. And I think we actually did this problem. Can I write it explicitly? Yeah. Y equals. Done. Go back. Use some of those rules we have. But take a look at this one. X cubed minus 2x squared y plus 3xy squared equals 88. Can we write this as y equals? And on first glance you say, well, what's the problem? Subtract x cubed from both sides. Okay, let's do that. So we'd have negative 2x squared y plus 3xy squared equals 88 minus x cubed. No big deal. Factor out a y. You got y's in both of those. Okay, let's do that. So then I have y, the quantity negative 2x squared plus 3xy, because that's a y squared there, right? Equals 88 minus x cubed. I don't want this. I want simply y equals. Can I do it? And there's no way. Okay? There's no way I can divide both sides by this, but then I've got a y on both sides. I don't want that. So what we have here is what we call an implicit equation, because I can't call it a function. Many of these problems that we're going to look at, their graphs are going to be maybe hyperbolas. The graph might be an ellipse. It might be a circle. They're not functions, okay? They're just expressions that we're going to look at. But if it's, let's say this is a nice, perfectly smooth ellipse there. Can you ever believe that? Anyway, imagine it to be an ellipse. Can I find a point on the ellipse? Yeah. Well, if I can find a point on the ellipse, can I find a tangent to that ellipse? Yeah. Whoops. Well, somewhere on there. If I have a tangent, can I find the slope of that tangent? So I can do all of these things even if I don't start with a function. So these things are not going to be functions, but I can still look at their derivatives. So here's what we have to do. Everything that I've ever tried to help you with about input, output, and making sure that you are aware where the input is in each of these notations and the output comes into play here. We are going to solve for dy dx. We're going to solve for that, okay? But it's not going to look like it at first. I've got 4 terms here. Everyone agrees they see 4 terms in this expression, this equation. So I'm going to take the derivative with respect to x. Now x is still going to be my input, mainly because the derivative I'm trying to find has x as the input of the derivative. So I'm going to use that for each of these. So I want the derivative with respect to x of x cubed minus the derivative with respect to x of 2x squared y plus the derivative with respect to x of 3xy squared equals the derivative with respect to x of 88. Now 2 of these you already know. 2 of these you don't have to think probably too much on. The derivative of a constant is 0. The derivative of x cubed is 3x squared. Okay, so those are going to be the easy ones. What we have to work on, and the implicit differentiation we work with, is with these items where not everything in the expression is the variable of the derivative, the input variable of the derivative. We're going to work with this one first. I see a product. Do you? Okay, I see 2x squared times y. So we're going to do it this way. We're going to take the derivative of the product. We have to use then the product rule on this piece. So I have, let's see, the first factor times the derivative with respect to x. And what's my second factor? Yeah, just y. Plus my second factor times the derivative with respect to x of 2x squared. And I'm going to put an extra set of parentheses in here just to make sure that we understand what all of that means. Okay? And I'm only working with that second term. I'm using the product rule. Now we'll go back and finish it, but for now we're just going to work with that second term. And so I have my 2x squared. This is the piece we have to really think about. I have a variable x. I have it with an expression y. Y is not x. Y is considered to be its very own function all by itself. And so what I really look at is the derivative of y with respect to x, and that should look somewhat familiar. Isn't that just one of the notations we use for derivatives? Yeah. And what are we trying to solve for? dy dx. So I'm very pleased that I have a dy dx. Now I hope I can say dy dx equals, when I'm finished with this, okay, plus y. Now what's the derivative of 2x squared? 4x. Okay, and we are done with that term because I have a dy dx here and I leave it just as you see it. There's nothing more I can do with it. Let's go on though. Plus, we're going to work with this third term. We're going to do the same thing with this. Do you see a product up here? Same as before. Okay, so we have to use the product rule. So we've got the first term, 3x times the derivative with respect to x of y squared plus the second term, y squared, times the derivative with respect to x of the first term. That's the product rule again, equals 0. Because the derivative of 88 is 0. Okay. When I start to work through this now, I've got my 3x. That's pretty easy to figure out. But when I look at the derivative of y squared with respect to x, y is not the variable of differentiation. Y is a function of itself. Do you see a composite function in there? The function y, because it's not the variable of differentiation, the function is squared. So it's a function within a function here. So I have to use the chain rule on that piece. So I'm going to have the derivative of the outside function. So if I'm looking at y squared as my composite, what's the derivative of the outside function? 2y. Times the derivative with respect to x of the inside function, which is, plus, and then I have y squared, and my derivative of 3x is just 3. That implicit differentiation, you have to keep your eye on what is the variable of differentiation. Every time you have an expression that is not matching that variable of differentiation, you have got to play with it, you've got to work with it as if it's a completely different function all of its own. So anyways, we got 3x squared minus 2x squared dy dx minus 4xy plus 6xy dy dx plus 3y squared. I think I'm okay on that. Am I? Eric, do you see something there?
No, you.
Okay.
I forgot you lost the calculus.
I did, yeah. If you like, I'll put them back in up here.
No, that's fine.
Well, I did it already. Okay. Yeah.
How come in the line above that was d dx?
So the derivative with respect to x.
Underneath that one. There are bits.
Here?
That's d over dx, and then underneath you say dy over dx.
From here to here?
Yeah.
Yeah, what's 3x times 2y?
Yeah.
Okay, that's 6xy. And then if I have the derivative of y with respect to x, that's the same as the derivative of y with respect to x. Now if I look at this, I can collect like terms. And I've got negative 2x squared dy dx plus 6xy dy dx. And I'll put the other terms on the other side, so negative 3x squared plus 4xy minus 3y squared. And now I can factor out a dy dx. And I can divide. I can separate, I can isolate, I can solve for dy dx. Now the difference with these derivatives from what we're used to seeing, we're going to have both x and y in these. Which means that if I have that parabola and I want to, or excuse me, ellipse, and I want to draw a tangent, I need to know both the input and the output in order to accomplish that. Otherwise, I wouldn't know which point, because there's 2 points that would share the same input. Okay, we are good to go.